Look closely at a modern commercial high-rise. On the south face, intense solar radiation is baking the glass. Deep in the core, a server room is generating intense internal heat. And on the third floor, a conference room is packed with 50 people. Every space has a different, conflicting energy state. Any air conditioning system has to achieve two basic objectives in these spaces. First, it has to control indoor air quality by replacing contaminated air with fresh outdoor ventilation. Second, it must control the thermodynamic properties of that air, specifically its temperature and humidity. If you only have one room to worry about, maintaining those conditions is a relatively simple engineering task. The complexity arises when you scale up. You have to satisfy 50 different, constantly shifting heat loads using a centralized primary plant. And you have to distribute that conditioning without sacrificing massive amounts of architectural space to ductwork. To solve this multivariable problem, engineers have to look past the physical sheet metal, the fans, and the chillers. They have to deconstruct the entire system down to its mathematical thermodynamic baseline. Despite the vast catalogs of equipment available, conditioning air ultimately boils down to manipulating just two variables: airflow volume and supply temperature. This equation represents baseline sensible heat transfer. Sensible load equals flow rate times specific heat times the temperature difference. Q represents the physical mass of air moved through ductwork. Delta T represents the thermal change achieved across the coils. Every HVAC system ever designed can be categorized by how it balances this equation. To meet a shifting load, the system must either modulate the flow of the air or modulate the temperature of the air. The most basic approach is a heat-cool-off system. It operates on a single control zone. As the demand in that zone changes, the system responds by altering the supply air temperature, varying the delta T, while moving a constant volume of air, Q. Because this setup is limited to one zone, applying it to a massive building requires a strategy to decouple the air generation from the individual rooms. This leads to the first multi-zone architecture, the dual-stream system. In this design, the central plant generates two parallel constant volume streams of air, one high temperature and one low temperature. These distinct streams travel through the building until they reach a terminal mixing box dedicated to a specific zone. The terminal box acts as the control point, modulating the ratio of the hot and cold streams. By blending the two, it achieves the exact temperature, the precise delta T, required for that specific room at that exact moment. While the dual-stream method successfully solves the multi-zone problem by varying the temperature at the terminal, generating and pushing two continuous, full-volume streams of air demands massive infrastructure and carries a heavy energy cost. A second multi-zone architecture is the reheat system. Like dual-stream, it relies on a constant volume of air and a variable temperature. This psychrometric chart shows the initial phase. A central air handling unit takes in a large volume of air and cools it deeply until it hits the saturation curve, intentionally condensing out the moisture. By driving the air to a fixed controlled dew point, the system guarantees that the latent load, the humidity requirement, for every zone in the building is satisfied simultaneously. Once the air reaches the individual zones, the secondary phase begins. Secondary heating coils warm that overcooled 55-degree air back up to whatever temperature is needed to satisfy the room's specific sensible load. This creates an operational paradox. The central plant is spending a massive amount of energy to chill the air, and then the terminal units are spending even more energy to heat it back up. Reheat systems offer unparalleled psychrometric precision for facilities with strict dew point and temperature requirements, but that precision comes with a severe thermal energy penalty. The dominant strategy in modern commercial buildings moves away from constant volume entirely. This is the variable air volume, or VAV, system. VAV inverts the thermodynamic approach. Instead of altering the temperature, these systems hold the supply temperature constant and vary the physical air volume, delta Q, to meet the load. The central plant supplies a uniform stream of cold air. As a room's thermal load decreases, a terminal VAV box mechanically throttles the airflow, reducing the volume of cold air entering the space. A pure VAV system has a strict limitation. It can either heat a zone or cool a zone at any given time, but it cannot do both simultaneously without being paired with auxiliary perimeter heating systems. The critical advantage of VAV lies in energy consumption. In most applications, the supply fans pushing the air consume more energy annually than the refrigeration systems cooling it. This graph illustrates the relationship between flow and power. It is highly nonlinear. As the required airflow volume drops, the electrical power needed to run the fans drops exponentially. By balancing the equation through delta Q instead of delta T, the VAV architecture trades absolute psychrometric precision for profound volumetric energy efficiency. These abstract thermodynamic manipulations require a rigorous physical architecture to execute. This schematic shows the layout of a central system draw-through air handling unit. Working from the outside in, the process begins at the intake. Air quality starts in the mixing plenum. Here, outdoor air combines with return air. The pressure drop through these dampers must balance the difference between the relief and intake plenums to ensure proper blending. The strict requirement in this section is the prevention of stratification. If parallel paths of unmixed air are allowed to travel through the unit, it will severely degrade the heat transfer efficiency downstream. The physical engineering of this mixing section establishes the exact thermodynamic starting line before the air ever reaches the coils. Moving downstream, the mixed air hits the filter section. This stage requires rigorous maintenance because a loaded filter increases system resistance and chokes the airflow. Next is the preheat coil, featuring relatively wide fin spacing. Its primary job is preventing the colder mixed airstream from freezing the coils behind it. Then the air reaches the cooling coil, which carries a dual mandate. It must extract sensible heat to drop the temperature and remove latent heat to extract moisture. To achieve precise dew point control, the physical design is critical. It requires a minimum depth of 6 rows and flat fins to minimize the bypass factor, ensuring untreated air cannot slip past. The final stage is the supply fan, which generates the static pressure to drive the conditioned air into the ductwork. It takes immense physical force to push this thermodynamic solution vertically through a building's infrastructure, fighting friction and gravity to reach multiple floor branches. Mastering the design of these systems requires translating abstract thermodynamic equations into a physical machine capable of meeting every dynamic load throughout the structure.